An F-15E Strike Eagle thunders through the night sky over the mountains of eastern Afghanistan's Gardez region, a labyrinth of underground caves where Osama Bin Laden and his Al-Qaeda fighters have vanished. Conventional bombs have proven useless against these natural bunkers. Insurgents simply retreat deeper into the earth, beyond the reach of traditional explosives. But this Strike Eagle carries something new. Developed in just 67 days during the frenzied aftermath of 9/11, this nightmarish weapon transforms oxygen itself into an instrument of destruction. It punches through rock and concrete. It can navigate tunnel systems, turn corners, and reach enemies who previously thought themselves untouchable. Tonight, beneath the Afghan mountains, this weapon will transform sanctuaries into tombs. An unconventional enemy. In the days following the attacks of September 11, 2001, U.S. military planners faced a major challenge as they prepared for what would become Operation Enduring Freedom, the fight to dismantle the Al-Qaeda terrorist organization that said it was responsible for the attacks and remove the Taliban from power in Afghanistan. They realized that they would be coming up against an enemy that would not fight conventionally. Instead, it seemed likely they would exploit the terrain to their advantage by retreating to Afghanistan's vast network of caves and underground complexes, some natural, others expanded and reinforced over decades of conflict. These weren't simple hideouts. Many dated back to the Soviet-Afghan War, when Mujahideen fighters constructed elaborate tunnel systems reaching hundreds of feet into mountainsides. These fortifications presented a daunting challenge. Standard air-to-ground munitions, even those designed to penetrate bunkers, could be unreliable or less effective in reaching fighters shielded by complex terrain or deep cover. The Pentagon needed something new. Thermobaric weapons. The solution would come from a concept military scientists had been refining since the Vietnam War: fuel-air explosives. Unlike conventional bombs that carry both fuel and oxidizer in pre-mixed form, these so-called thermobaric weapons dispersed a cloud of fuel that mixed with atmospheric oxygen before detonation. The result was an explosion with devastating effects, particularly in confined spaces. Early fuel-air explosives, like the CBU-55, had been deployed in Vietnam to clear helicopter landing zones by instantly flattening sections of jungle. Throughout the Cold War, both American and Soviet military scientists continued refining thermobaric weapons. By the 1980s, the U.S. had developed second-generation fuel-air explosives, including the BLU-73, 95, and 96. These weapons saw action during Operation Desert Storm in 1991, where U.S. Marines dropped 254 CBU-72 fuel-air bombs, primarily from A-6E aircraft, targeting Iraqi personnel in trenches and clearing minefields. Meanwhile, Soviet engineers were creating their own advanced thermobaric arsenal. The RPOA Shamel rocket launcher, first deployed in Afghanistan in the late 1980s, demonstrated the devastating effectiveness of these weapons in mountainous terrain. Russian forces would later employ similar weapons to devastating effect during urban combat in Chechnya in the 1990s, proving their utility in both confined spaces and built-up areas. A new bunker buster for a new era. By the late 1990s, the Defense Intelligence Agency was closely monitoring thermobaric weapon developments worldwide. A 1993 DIA study titled Fuel, Air, and Enhanced Blast Explosive Technology, Foreign, detailed how these weapons had evolved from simple fuel-air bombs to sophisticated enhanced blast munitions using advanced energetic materials. What military planners now envisioned, however, was something more specialized, a weapon that combined the penetrating power of a bunker buster with the enhanced blast effects of thermobaric explosives. This would allow them to reach protected targets deep underground before unleashing a destructive pressure wave that could navigate through complex tunnel systems. When terrorists struck on September 11th, the theoretical need quickly became urgent. Exactly 1 month later, on October 11th, 2001, the Defense Threat Reduction Agency formed a quick response team, bringing together experts from the Navy, Air Force, Department of Energy, and private industry. The team faced extraordinary pressure. While standard weapons development often took years, they had weeks. Working around the clock, explosives experts at the Naval Surface Weapons Center in Indian Head, Maryland, began formulating an enhanced explosive fill that would generate higher sustained blast pressures in confined spaces. Meanwhile, Air Force engineers at Edmond Air Force Base in Florida tackled the challenge of modifying existing delivery systems and fusing mechanisms. Their starting point was the BLU-109, a proven bunker buster that had been in service since 1985. Its hardened steel casing, approximately 1 inch thick, could penetrate 6 feet of reinforced concrete before detonating. What emerged was a lethal adaptation that would become known as the BLU-118B. At first glance, it looked identical to the conventional BLU-109, sharing the same exterior dimensions and weight of roughly 2,000 pounds. This identical exterior meant that no modifications were needed for the aircraft carrying it, a critical factor, and speed of deployment was essential. Inside its armored shell, however, the BLU-118B contained an advanced thermobaric fill composed of PBXIH-135, one of the Navy's insensitive polymer-based explosives, and HAS-13, a solid fuel-air explosive. The weapon's lethal mechanism was designed to operate in multiple phases. First, its hardened steel casing would allow it to penetrate fortified surfaces, such as cave entrances or bunker walls, before a short 120-millisecond delay would trigger the main charge. At that point, the thermobaric fill would disperse into the surrounding space, mixing with atmospheric oxygen and then igniting. The resulting explosion would produce a fireball and a pressure wave significantly more powerful than a conventional blast of the same size. In confined environments like caves and tunnels, this overpressure wouldn't just detonate in a single burst. It would linger, bouncing off surfaces, flowing around corners, and propagating through complex passageways. A vacuum effect would follow the blast, as the fireball would rapidly consume oxygen in the area, a secondary mechanism that would eliminate anyone who would survive the initial detonation. Delivery and testing. With the new weapon almost ready for testing, military planners turned to the question of delivery. The BLU-118B would require a platform capable of precise targeting that would be able to navigate Afghanistan's challenging mountain terrain, and that had the payload capacity to carry the 2,000-pound weapon. The answer was the F-15E Strike Eagle. First deployed in 1988, the Strike Eagle represented a radical departure from the original F-15 design philosophy. While the F-15 had been conceived as a pure air superiority fighter, built under the mantra, "not a pound for air-to-ground," the F-15E evolved into a multi-role aircraft. With a combat range of nearly 800 miles and the ability to carry up to 23,000 pounds of ordnance, it was ideally suited for long-range strike missions. Unlike single-seat fighters, the Strike Eagle featured a 2-person crew, a pilot in the front seat and a weapons systems officer, or WISO, in the rear. This configuration proved invaluable for complex bombing missions, allowing the pilot to focus on flying while the WISO managed targeting systems and weapons delivery. The aircraft was equipped with the low-altitude navigation and targeting infrared for night system, or lantern, which allowed it to fly at low altitudes in darkness and adverse weather conditions. By December 2001, barely 2 months after the BLU-118B project had begun, the team was ready to use the F-15E to perform a live test. At the Nevada test site, the aircraft dropped a prototype onto a tunnel complex, similar to those expected in Afghanistan. The weapon skipped into the tunnel entrance and detonated with a delayed fuse. The results dramatically proved how effective this new weapon was. Compared to standard explosives, the new thermobaric fill generated significantly higher overpressure throughout the tunnel system, with lethal effects extending far beyond the blast radius of conventional explosives. On December 21st, Undersecretary of Defense Edward C. Aldridge made the official announcement. The United States had created a new thermobaric weapon specifically designed to attack tunnel complexes in Afghanistan. Its development, from concept to combat ready, had taken just 67 days, one of the fastest weapons development cycles in Pentagon history. 10 of these weapons were immediately made available to the U.S. Air Force. They would now be put to the real test: combat deployment. Afghanistan mission. By early 2002, intelligence analysts had identified a prime target for the new weapon, a cave complex in the Gardez region of eastern Afghanistan, where Al-Qaeda and Taliban fighters had taken refuge. This wasn't just any cave. It represented the type of hardened, protected target that had frustrated conventional bombing efforts in the preceding months. For this mission, The F-15E would carry the BLU-118B, configured as a GBU-24HB, the thermobaric bomb body fitted with the Paveway 3 guidance kit. This laser-guided system provided the precision necessary to place the weapon exactly where it needed to go. The mission was assigned to the 335th Fighter Squadron from the 4th Fighter Wing, known as the Chiefs, operating out of a forward base. Detailed planning revealed the mission's extreme complexity. The cave entrance was partially obscured by a ridge, creating a narrow corridor through which the weapon would need to travel. Captain Randall Haskin, one of the 4th Fighter Wing pilots involved in the mission planning, later recalled the sobering assessment, explaining, quote, "The margin for error was anticipated to be only 25 degrees. That margin was pretty small, all things considered. My ops officer was at the Combined Air Operations Center when the mission was being planned, and they knew that there was a pretty significant possibility that it wouldn't work. A 50% chance, if I remember correctly, was what he told the commander who was overseeing the operation." In the early hours of March 3, 2002, the Strike Eagle took off, carrying the first BLU-118B ever used in combat. The approach to the target area required careful navigation through Afghanistan's mountainous terrain. As the F-15E neared the target, the crew prepared for the precise weapons delivery that would be required. The Wizzo locked the laser designator onto the cave entrance, painting it with an invisible beam that would guide the bomb to its destination. In the critical moments before release, the pilot executed a maneuver that would have unforeseen consequences. Seeking a better angle for the Wizzo to acquire the desired mean point of impact, the pilot performed a last-second bunt, a pushing of the aircraft's nose down to delay the bomb release. This was a standard procedure for conventional laser-guided bombs, allowing the Wizzo to get a clearer view of the target. What the crew didn't anticipate was how this maneuver would affect the sophisticated Paveway 3 guidance system. The weapon was designed to select its flight mode based on the aircraft's attitude at the moment of release. When the F-15E's nose pitched more than 5 degrees downward, the guidance system automatically switched to a different delivery profile than what had been planned. The bomb released from the aircraft and initially tracked toward the target, its guidance system following the laser energy reflected from the cave entrance. But the altered flight mode meant it followed a trajectory different from what mission planners had calculated, one that couldn't navigate the narrow 25-degree corridor to the target. Seconds later, instead of penetrating the cave entrance, the BLU-118B struck the very ridge it was meant to avoid. The first combat use of the United States' newest thermobaric weapon had ended in failure. The mission's outcome revealed a critical lesson about advanced weapon systems. Even minor deviations from planned parameters could have significant effects on performance. The automatic mode change triggered by the pilot's bunt maneuver, something that would have been inconsequential with many other weapons, proved decisive with the sophisticated GBU-24HB. Continued use. The failure of the first BLU-118B mission in March 2002 could have relegated the weapon to the status of an experimental curiosity. Instead, it became a lesson in the complexities of deploying advanced munitions in combat conditions. Rather than abandoning the concept, military planners analyzed what went wrong and refined both the weapon and its delivery techniques. The lessons from the first mission were straightforward. The narrow margin for error required absolute precision in both planning and execution. Future missions would incorporate more detailed terrain analysis and stricter parameters for pilot maneuvers during the critical moments before weapon release. In late 2002 and early 2003, during operations in Afghanistan's Tora Bora region, military reports indicated that thermobaric weapons were successfully deployed against cave complexes where high-value Al-Qaeda targets were believed to be hiding. Unlike the initial mission, these strikes benefited from improved delivery techniques and more favorable target geometries. After-action assessments described the weapons as highly effective, with pressure effects reaching deep into tunnel systems where conventional bombs had previously shown limited results. By the time Operation Iraqi Freedom began in March 2003, the BLU-118B had evolved from an experimental weapon to a specialized tool in the military's arsenal. As coalition forces sought to neutralize Saddam Hussein's regime, intelligence identified numerous hardened bunkers and underground command centers as priority targets. With its unique capabilities, the BLU-118B was the natural choice for several of these facilities. The BLU-118B's development also influenced military thinking about other difficult target sets. Its success in reaching protected spaces led to further refinements in the broader family of thermobaric weaponry. Smaller, more tactical variants began appearing in the United States arsenal, including the AGM-114N Metal Augmented Charge, or MAC Hellfire missile, which incorporated thermobaric elements to enhance its effectiveness against bunkers and buildings. By 2004, U.S. Marines in Iraq were using the shoulder-launched multi-purpose assault weapon Novel Explosive, or SMANI, featuring a thermobaric warhead during urban operations in Fallujah. One Marine team reported destroying a large one-story masonry building with a single round from 100 yards away, demonstrating how thermobaric technology had evolved from the large BLU-118B to more tactical applications. With the increasingly wide range of thermobaric options available, military doctrine evolved to incorporate these new capabilities. Training programs for forward air controllers and joint terminal attack controllers now included specific modules on thermobaric weapons employment, with emphasis on their unique effects and optimal target selection. From concept to combat in just 67 days, the BLU-118B program became a model for accelerated weapons development in response to urgent battlefield needs. Ethical considerations and controversy. As thermobaric weapons like the BLU-118B became more prominent in U.S. military operations, they also attracted increased scrutiny from human rights organizations, arms control advocates, and international observers. The same characteristics that made these weapons militarily valuable, their enhanced lethality in confined spaces, raise questions about their humanitarian implications. Human Rights Watch, in a report published on February 1, 2000, highlighted concerns about thermobaric or fuel-air explosive weapons. The report also referenced a 1990 CIA study that provided an equally sobering assessment, quote, "The effect of an FAE explosion within confined spaces is immense. Those near the ignition point are obliterated. Those at the fringe are likely to suffer many internal, invisible injuries." Despite these concerns, thermobaric weapons remained legal under international law. Unlike chemical or biological weapons, which are specifically prohibited by treaties, thermobaric weapons are classified as conventional armaments. In 1980, Mexico, Switzerland, and Sweden presented a joint motion to the United Nations to prohibit thermobaric weapons, but this effort was unsuccessful. Later attempts by the United Nations Institute for Disarmament Research around 2010 to categorize and regulate enhanced blast weapons similarly failed to gain traction. Military officials maintained that while the effects of thermobaric weapons could be severe, they were no different in principle from other conventional explosives. They argued that in many scenarios, these weapons actually reduce civilian casualties by allowing more precise targeting of enemy combatants in protected locations, eliminating the need for larger conventional bombs that might cause wider collateral damage. A 2015 article on America's thermobaric arsenal by Dave Majumdar explained that both the thermobaric Hellfire and the SMANI were specifically developed for the Afghan war. The article referenced a Marine Corps Gazette essay describing how Marines use these weapons tactically. According to the Marine Corps publication, units would employ blast weapons before entering structures that had been converted into defensive positions. The Marine Corps justified this approach by noting that replacing damaged buildings was less costly than risking American lives, and that all battalions adopted appropriate blast techniques when approaching what were effectively bunkers with unknown occupancy. The same article acknowledged criticism of these weapons, but noted, quote, "While thermobaric ordnance are legal in combat, many non-governmental watchdogs have condemned the use of them because such weapons tend to be indiscriminate. But war is not a clean business, even under the best of circumstances. There are instances where the U.S. military has no choice but to use thermobaric weapons. Otherwise, the troops would be placed in unnecessary danger, or terrorists might be able to entrench themselves in caves or buildings, like in Afghanistan. At present, the BLU-118B exists in this gray area, legal under current international law, militarily effective in specific scenarios, yet for many, troubling in its human effects. Going forward, the controversy surrounding thermobaric weapons reflects a broader question about the ethical implications of the increasingly powerful tools of warfare.